I can't really talk today, so there's going to be a lot of writing on the board and not a lot of explanation. Still, I can ask questions. We're doing much simpler material today than last time, but I don't have much here to work with. So, by the way, does this marker work?
It works. Also, I think I have extras.
I have extras. All right, so we're here. All right, we figured out last time this is a metric. I'm going to run through a few other properties that are going to be important for the applications. Much simpler than what we did last time. So first of all, how does this behave? I'll focus on W2 in particular, but you see similar things with WP. So say this is my F, and this is my G. So what does L2 care about? L2 cares about really this distance, right? Whereas W2 is interested in this. So I think Sant'Ambrogio called W2 a horizontal metric, and L2 a vertical. But what happens with some different cases? What if they're close together? Here's F, here's G. So say we shift this by a distance S, then this vertical distance is also going to scale like S. Okay, so if we do this, so what are we doing? We're on the order of S. Right, and we're integrating something on the order of S squared over an order 1 area. So this feels like order S at the end of the day. If the profiles are close together. And what about W2? Well, this is going to take this and just shift it a distance S. So it's going to be distance squared. Also order S. So actually, if these things are close, L2, W2 behave the same, basically.
So is it obvious that this should be S squared F? Is that
So what's the transport map here? Right, so then we're looking at, if we're doing W2. That's close together. So if they're close together, we don't really get any gain over L2, which is easy to use. What if they're far apart? Okay, so here's my F. Here's my G. Okay, so what are we going to get? We're going to get again. But now there's no overlap between these two. Right, so we're just going to integrate F squared, and then we're going to integrate G squared. So this doesn't, L2 does not actually see the shift at this point. There's no information here about how big the shift is. Just, they're not on top of each other. Whereas W2 is going to do what it did before. Right, it's going to say, okay, what's the shift? X plus S. Nothing rigorous, that's just a little bit of intuition into what this is trying to do. All right, another interesting, or even important property for the applications. Here we have to raise it to the pth power. Right, so let's just to not write these things over and over again. Maybe let's start like this. So let's check the marginals. We know the marginals of the originals. Okay, so with a feasible plan, we can at least estimate this. Well, not equality. All right, so let's put this in. And these guys are optimal. So here. So convexity will be important if we ever want to minimize this thing. Another nice property in the real world is how this thing deals with noise. Okay, so here's my F. I add some high frequency oscillations to it. So these are actually order 1 oscillations. So what does L2 do? Okay, what about Wasserstein? Wasserstein looks for a map. All right, now with these oscillations, some mass has to move a little farther than it did before. Some mass maybe a little less far. Overall, the map is not going to move things very far. Right, we're not looking order 1 here. We're looking small changes here. So in other words, if you had high frequency oscillations here, even large amplitude, Wasserstein doesn't care, it doesn't really see them, right? This difference between these, even though these are very high peaks, is going to be small. And that exercise you're going to do actually in your next homework, I think. But you can do this not just for a sine wave, but for actual noise. For random noise. Okay, so let's say we take G and add some noise. Okay, so chopped our domain up into n pieces, and in each one we randomly pick from a uniform distribution of value for the noise. Okay, again, these are order 1 oscillations, but the map doesn't have to change much. And you can put estimates on it, and with the estimates you get I have to renormalize this.
What notation is that?
This is the average of Fn, right? Because these have to have the same mass, and adding noise changes the mass. Okay, so what does this say? This says if we have very high frequency noise, so n is large, right? So the noise is just random everywhere. Then Wasserstein doesn't really see it, right? The distance between these is basically the same as the distance between your original F and G, which can be useful in applications where your data is really noisy, and Wasserstein somehow filters that out and says, let's just look at what's important underneath there. And this proof, I'm not going to do here, but I posted the paper on Canvas. It's So this result came out of actually an application paper, and it's this application that I want to go to next that's motivated a lot of this work, and results on the Wasserstein distance.
So is that essentially that you're taking the square of the Wasserstein norm with F and renormalized?
That's right, the square of the Wasserstein distance.
So in essence, that's just the Kantorovich problem.
It's just the optimal value for the Kantorovich problem, exactly.
Expectation of that.
That's right.
Okay.
So I'm going to at least introduce this problem a bit today. Seismic full waveform inversion. Here's the goal. We want to know what's under the Earth's subsurface. Right, so here's the Earth's surface, and down here there's different materials, different layers, maybe a deposit of some mineral. But we're up here, we can't see what's down here. So without sending ourselves down there, we've got to send something down there to investigate. So we send a sound wave. So here we are again, there's surface. And there's a nice truck. The truck goes boom, boom, boom. Or maybe it's an explosion, or it might be offshore a boat producing this sound wave. And out here we have receivers. And what happens? The sound waves come down here, they hit this layer, and there's reflection, refraction. Eventually they get picked up by these receivers sometime later. I'll call this distance to each receiver is S. All right, so what do we know? We know the amplitude of the wave at each time t at each receiver S. So what we're going to get is a picture that looks like this. And it's usually drawn upside down. I don't know why. And the farther away, I mean, as a very crude estimate right now, the farther away these are, the longer it takes for the wave to get there. And it will come with some amplitude. So we get some data. And now from here, we want to figure out this. Obviously, the actual pictures you get here will be much more complicated when there's lots going on down here. So So what equation is this data really coming from?
Helmholtz equation?
Okay, yeah, Helmholtz equation or a wave equation, exactly. So the data say a wave equation. So if I write my domain like this, here's my truck. Okay, and what's U naught? U naught is the signal generated by this truck here. And we have initial conditions. And nothing's happening. So whatever's going on in here, or whatever's going on in here, that eventually produces this picture, it's really being determined by this velocity field here. So it's this velocity field that holds the key to what the structure is down here. It's that we want to find. Okay, and what do we have to work with? We have to work with this, which is a surface measurement. So for z equals 0, we know the solution. Now, if I wanted to go the other way, it's easy. So the forward problem is this. So the forward problem, I know the velocity field. That is, I know all this structure. I solve a wave equation. I think this is giving up now. Okay, and I can easily read off the surface measurements, whatever they are. Oh, sorry, this is time. Okay, so for a given velocity field, if you give one to me and just say, what would this produce? I'm going to call that f of v, and it would produce some picture like this. And I can do that. I just have to solve the wave equation. Now, we want to go the other way. So given an observation, Okay, so we're given this. The question is, from there, can we get to here? All right, this is the notation I'm using. G is my observed data. I have no control over it at all. F of V is my simulated data that you gave me a velocity field. I solved the wave equation. This was the surface measurement I pulled off of it. So there's just a couple comments. An obvious question, hopefully. So if you give me a G, does there exist a V that would have produced it? That's important, and I'm not going to say anything more about it. And there's plenty of literature available on these questions. And secondly, this is what your initial profile would often look like. Something like finally, in the real world, this G came from a velocity field, but there's noise, there's measurement error, there's whatever other junk is going on. So it may not correspond exactly to the F that we're going to try to find. So ideally, we'd want this. Given G. Right, given this data, let's find the velocity field such that the simulation exactly matches the data. That's the best we could hope for. Now, knowing that this may not be well posed for any number of reasons, noise being one of them, we're going to relax this. All right, what's the easiest choice of distance you could think of to put here?
L2.
2, yeah. That's the first thing that everybody tries. There's no point in pulling out fancy, complicated tools if you don't need them. Or L2 squared. You know, L2 squared typically will behave better. So let's try this. All right, let's just do a little toy example. A single reflection. Okay, that's about as easy as I can make it, I think. So where are we? Here's my truck. Here's my receiver. This is my distance, S. And I'm assuming this happens. And V is constant. So what are we going to read here? What is this signal going to look like? So say I send in a Ricker wavelet here. and I just have this single reflection, what do I get out here? The same thing, yeah, just time delayed, right? So we'll write it like this. F of v, which is a function of t. If I choose my length scale right. And we observed that's what we observed, but with the correct velocity. So now we want to somehow minimize the distance between these two over v, or possibly over 1 over v, because it's not nice having that in the denominator there. So okay, so let's try to plot these. So I have one of my signals. Right, this has the correct shift. And then this one is shifted depending on what value of v I put in. So this might be okay, and this shift is going to look like 1 over v minus 1 over v star in magnitude, depending on which is bigger. So now we've got profiles that look like this. This is what you could see in practice. And we want to, okay, we're going to take the difference of them and take the L2 norm and try to minimize it. So what is the objective function that we're actually trying to minimize? If we try to plot it, and here we have, well, if they're too far apart, they're going to be constant, right? We saw that before. If things are too far apart, L2 doesn't care anymore. It just gives up. So we're going to be here. We're going to have some little dips depending on whether different peaks overlap. So, you know, when this left peak overlaps with this right peak, that's going to, L2 is going to say, oh, they look a little closer now. So the distance goes down a bit and then it comes back up. Now eventually it actually hits the correct value where they overlap. And then it does the same thing in reverse. So if I ask you to minimize something that looks like this, are you happy? Why not?
There's local minimums, so I'm getting the right one.
There's local minima, exactly. So minimizing this is hard. Okay, and this phenomena in this application is known as cycle skipping. This is where you do your optimization, and it terminates by deciding, let's let this little valley and this little valley overlap. So it doesn't quite get them on top of each other. But that's the local minimum, so the algorithm says maybe I'm done. So this is a big issue. So L2 is easy, but it doesn't work very well. So this was an idea we proposed a few years ago. Maybe instead of L2, we could use some kind of Wasserstein metric instead. And I did some toy examples where we saw that, okay, with profiles that are close together, W2 is going to behave like L2 and kind of do what you want, but as things pull apart, we shouldn't get this kind of cycle skipping. W2 is still going to see that there's a shift happening. Right? And that's exactly what happens in this example. So this is the idea. So let's try D of G is equal to the squared W2 metric between them. If we do that here, okay, we're going to compute a transport map between them. The transport map is going to shift things by exactly this distance. This is just a constant shift. Okay, so then if we look at this as a measure of misfit, what do we have? We have T minus this squared. Okay, and if we assume that F is normalized out of mass 1, then this is nothing but the square of this shift. Okay, so over here you said you didn't really want to minimize this. But if I plot W2 for you, okay, so again, I'm going to plot against 1 over V. As a function of 1 over V, this is just a parabola. And it's just shifted over here. With its minimum where you want it. If I asked you to minimize this, would you be happy? Yeah, probably, right? This is the easiest thing you could hope for. This was a toy example, of course. But it turns out, and we'll talk more about that, Wasserstein has great properties for minimization for the kinds of things we expect in this particular application. So, 1 or 2 remarks. The data that we get out of these problems is not a probability measure, presumably. So some pre-processing is needed on the data. So there's different things that one can do. One option, if you're given data, is to look at the positive and negative parts separately and rescale them. So you might say, let's look at this. So the positive part of F and normalized compared to the positive part of G. And then do the same thing for the parts that are below 0. You could just sort of square the whole signal. There's different things. You could take the whole thing and just sort of lift it up. So there's options. You have to do that, but it works okay. What's my other comment? My other comment was, you're not always going to get a parabola when you do this in real life because there's more than one variable that you're trying to solve for. Much more complicated circumstances. So in reality, you have a whole velocity field you're solving for. You cannot show that Wasserstein is convex with respect to every perturbation you might come up with, but you can look at the perturbations that are kind of natural in this problem and show convexity with respect to those. So I want to do a few of those results, but I think I'm going to stop early today and do that next time.